Welcome to the third sliding window problem in Blind 75. And in this problem, given an array of strings, in this case, let's just use a random array of strings or a list of or a string, generally speaking, right? Not an array of strings, so just a string. Given a random list of strings, it's like this. Given this array of string, we need to basically given a string of uppercase English characters, which means there are only 26 characters that we need to go capital A, capital B. Given that, and given an integer k, which basically tells us, how many characters we need to replace, or just a quantity of a numeric quantity that tells us the amount of actions that we can take on this string. Uh, we replace that character in the string with any other uppercase English language, right? So potentially, this gives us the number of actions that we can take, right? This is the number of actions we can take and by action, that action is to replace the value of any replace the value of any character within the string to another value, basically. So we take action to replace another replace any of the words in our string by any other capital letter, basically. And that's what comes here. There are only 26 letters from A to Z. So if we're given the amount of actions we have, right? We have only two actions. So we can replace any two values in this list of or this string of five uh, characters to any value, basically, any letter from capital A to Z. This is our range. This is basically our range that we have for any action that we want to take. So this is the range here. Given this range, we need to understand how we can potentially replace these characters. Now, given these specifications, we need to understand exactly what we need to do with these actions, and that's clarified here. After performing the k replacement, return the length of the longest substring, which contains only one distinct character. So what does this mean? So given these constraints that we have, given these constraints for action, we need to change the value. Given these constraints, we need to change the value from this string here, such that we can create a substring. We can create the longest substring which has the same value within that. So what do you mean by that? So if we have three A's, rather two A's, I'm just going to rewrite the substring I wrote before. Two A's, a B, another A, and then another B. We need to identify the longest substring we can create, given that the value of K that we have is 1. So only one action we can take. So given that, how long a substring we can create with just has A or just has B in it, right? So in this case, the longest substring we can have is basically n equals to 4, right? Because if we change B here with an A, right, just one action, we can have the first four characters as our uh, as our substring that contains all of the same letters. So that is basically what we need to do in this problem. So Given that, given that basically, let's go over another problem. So we have here for another string potentially. I'm just going over this so you can understand with x, y, y, x, and the actions that we can take are only two. Given k is 2, right? What is the longest substring we can create? Quite easy. We can replace this y into x, that's first number one action, and we can replace this y with an x as well, that's the second action. So we have no more actions left, and all of these four become strings. So this entire is the substring with the longest amount of the longest substring we can get with the same characters. So the answer becomes 4. So that is all we need to do in this problem. Potentially, if we talk about the time complexity of this problem, uh, we can say it's O of n, but to be exact, the solution that we're going to discuss is going to be O of 26 into n. And why are we mentioning 26 in specific? Because 26 are the number of capital letters we have. 26 are the capital letters we have when in the alphabets from capital A to Z. That's why we're using the quantity 26. We can potentially get this done into get a solution that's only O of n, but again, like that is a solution that's relatively complicated, and it's rather very complicated solution to get to that particular time complexity. So we'll not be focusing on that in this video. We'll be focusing of a solution that's as close to which is as close as what we need and what would be acceptable as a solution to this particular problem, which is which is what we're going to discuss right now. So given all of this, what is going to be the solution for this problem? So there are 5 potential steps in this problem that we need to go with, right? So let's write down a simple array again. So x, y, y, x. So let's just use this again, right? Given this string, we need to create an algorithm that basically finds that substring, right? So a best solution for this could be the sliding window problem that we discussed, and that is basically the nature of this problem. Any problem that wants you to create a sliding window, a substring with certain filtering or certain changes is 9 out of 10 times the sliding window problem. So potentially a solution to this problem could be, right? We have two windows, two values, left pointer and right pointer, right? They point to each other, right? We have just one here. At the same time, we build our hash map, which contains the more maximum frequency of each of those letters. So the maximum frequency of x, maximum frequency of y, right? So we say we basically run the algorithm and count right now how many x's we have right now. So we have one x here, and we have 0 y's, right? So it seems that this can be extended, right? We don't need to take any action here. So we extend this window to y, right? And bring the right pointer here, right? So we have y here. So we have one y, one x. So we change this value to as well. I think it's still within our range. So let's cancel this out as well. So or rather, yeah, let's cancel this out as well. Freeze it one more time. Bring right here. Again, we cancel this out because now we have two y's, and then we can cut this up and move the right pointer again. There are two x's. Bring two, right? This is how this is one way we could do this. But I think the better way for us to solve this problem would be, let's remove this first. Let's remove these here, right? Okay, take our pen back here. So better thing that we can do is we can cover the entire length with our sliding window. The right pointer here, the left pointer here, right? Once we have that, what we could do is, given we have the potential of action is 2, right, for us, given the potential of action is 2, uh, we can do a simple check with the formula to help us identify, basically, right? So the formula for this case is the length of the window minus the count of the most frequent character. So the most frequent, so both are 2, right? So the length, this is the formula we need to use at every stage of this particular, uh, you know, uh, uh, this particular problem when we move the sliding window to check whether it fulfills our requirements, right? Minus the most frequent character value. We have 2x and y, both are most 2, so like that's going to be our value, right? So in this case, we have 4 as the length minus 2, and this answer, basically, whatever the answer here comes to, it needs to be basically greater, less than, equal to the value of k, right? So as long as it is equal to k or less than k, this particular window would be our solution to the problem. So in this case, this becomes 2, and 2 is equal to the 2 actions we have. So this probably is the solution, and as you can see, this does make sense. But potentially imagine we don't have 2 actions, we just only have 1 action, right? So this is greater than that, so this becomes the wrong answer. So an easier mechanism for us would be to move the left pointer instead of the right one and move it one step here, right? Now we have y, y, x. So potentially, again, we have 3 elements in our sliding window. We deduct 2 as the most recurring character. Our answer is 1. Yeah, that seems to fill in our domain of in our constraint requirements like here, right? As we can see, this formula is the constraint requirement for this particular problem, and this particular formula is used to solve this problem, basically, right? So considering that we have this particular problem matches the constraint of being less than equal to 1, which is the value of the renewed value of k, right? This could be the answer. And how can we make this an answer? We can replace x here with a y. X can become y. Those are the 3 substrings, which means the longest answer would be 3. So that is basically logically how this question could be answered. And again, the time complexity for this is of O of 26n. But this is basically the most optimized answer we can do without unnecessary, optimization. So with that out of the way, let's try to code this problem out. So let's first, uh, yeah, let's start coding this problem. So first thing we need to do is in this problem is to set up our count mechanisms, right? We need to we need to set up the trackers for the sliding window. We need to set up the tracker for the maximum length. We need to set up the tracker for maximum frequency, and we need to set up the tracker for the counts that we're going, uh, use to track the count of characters in the window. So let's just set that up. So we're only setting one pointer for the sliders because we're going to move the left pointer based on our formula. Maximum length stores the maximum length of the string, and maximum frequency stores the amount of the character with the most recurring characters within that. And count is going to restore our count. That out of the way, the next thing we need to do is basically write down our logic for this within a for loop where we iterate through and move this particular problem, right? So our iterable is going to be the right. So we're going to write that out. With that out of the way, I think we need to make it so that we're able to iterate over that particular problem. So with that out of the way, Now we need to update the count of the current character. We need to identify how many of a certain character are within that particular problem. So let's write the code to do that. So we're basically writing the code to update maximum frequency as well. All right. So now we need to write the next part of the code logic, which is basically uh, a decision-making loop where we check if the number of replacements required exceed k or not. If it exceeds k, we shrink the window from the left side as we discussed and showed in the logic that we covered. For that, we're going to write an if statement to sort that out. The last is where we update the max length of the current window size within this loop. With that, I think we can exit this loop and just return the maximum length back from this function. We can run this code, see if this solves the problem. And that solved both cases. And that is how you solve the longest repeating substring problem with replacement, a problem in the blind 75 list. This is the third problem. in the sliding window problems. So with that, we're going to wrap this video up. If you got any value from this video, please like and subscribe, and we'll see you in our next video. Thank you.